So this, as promised, is about DigDug. Now, I've just... oh, Canada last week, right, okay. I have managed to get it sort of working, but I wanted to explain some of the major problems I've had with it. It's not been as straightforward as say Grid Runner or even Myriad. I mean, Myriad was pretty straightforward. This has been an absolute pain up the butt. So what I thought, hello, so seeing as that Docster's been pestering me for this, I thought I'd just run through what I've been up to. I mean, I've just literally got back from the coast, what, an hour ago. And before setting this up, so this is what this week's all this stream's all about. So I've put Myriad to one side, and we are going to look at DigDug. Now, DigDug itself is trying to find the file now. I can remember the game in the arcades, but I never played it as a child. I don't know why. I think it was Defender that was, and Phoenix. They were the ones I played all the time. Hang on. So let me see if I can show you what DigDug's supposed to look like. So let's fire up C64. And see if I can load it. Right, DigDug. So this is DigDug. Right, so 2 characters, change difficulty. I don't know what this change in difficulty is. And we got carrot. Whatever that is. That's a mushroom. What is that? Is that gherkin? Looks like a plum. And then whatever that is. So there are your difficulty levels. So that we're going to stick on the easy one because I'm no good at this thing. And then try it. Now, if you notice, there's pauses. Yeah. Oh, I was going to say. And must be a different joystick. There we go. So I don't know how this works. I don't know how to play this game, so I'm absolutely rubbish at it. But there is a pause. So initially, let me see if I can get the. Do I have the original? What's that one? That's the original, right? When you if you use Infiltrator on the PRG, so let me fire up Infiltrator. I don't know why it goes over there. Right, PRG, DigDug, where are you? Disassemble. Off you go. So it's doing it. And we look at it. You can see everything is in the almost in the first. What's that? 16, 4, 8, 16k. So it starts at the typical start point, 0800. But what it's doing is it jumps to the restart. So that's the restart vector. And what it's doing, it's copying from where the end is. So 4738, that's it. 4738 is actually the end of this game, which is roughly about there. So it's copying from there backwards, yeah? And it's storing it in, if I can find it, you know what, BF00. So it's copying it to here backwards. So when you look at it, it is, what's that, 4, 8, 12, yeah, 16, it's a 16K game near enough, and it's the first thing it does is relocate it to there backwards, so 1, 2, 3, 4 to here. So it copies the whole thing up from BF, well, 4738, that goes to BF00, and then it copies it backwards until it hits about 8000. And then what it does is it then jumps to reset. So it resets the 64. So as soon as it loads in and runs, it copies it up to the high memory underneath basic as well, and then does a soft reset. And what's happening is that the I think it's here, yeah, here, this is where it copies to, yeah, and this, if you remember when I was doing the graphics extension, is the indicator for the ROM to say, oh, I've got a cartridge in place, I will run that. And then it looks at the vectors on the cartridge, which are there, I think that's it, and it then jumps to those vectors and then runs the cartridge. And basically what they've done is they've converted a cartridge game to load off tape. So there's been no extra development for this game. The game must have been a cartridge game to start with, and they decided to put it on a tape, and all they did was devise this copier. So you load the entire game in, it immediately runs, and then copies the whole lot into the correct location, and then resets the 64, and then the 64 thinks it's got a cartridge in place. So after I'd infiltrated this whole thing and then started looking at it and realised, oh rats, it relocates. So what I did was then force a breakpoint here, force a breakpoint in Vice here, and then run it again. This time I then in Vice saved as a binary file the memory from 8000 to C1000, and that is what you see here. Right, so this is the original DigDug being relocated. So here's the cartridge marker. So this is what it's saying, start at 8009, which is here. So this is the start point, and then run through that, and that's how it starts the game. But after converting it to kick, getting rid of all the errors, you know, all the memory errors, so you know where it's where you've got a 0-page instruction but to 4, so it's a word instead of a byte, having to convert all them into words and stuff, so you get the byte count exactly the same. We still had a problem. So this is the original. I'm just wondering whether I should do what I've just said so I can show you what the issue is, because I didn't keep all the different states, I don't think. So have a look. Did I keep the different states? No, I didn't. Ooh, maybe. Aha! Yes, I did. So that's the original state. So this, if I let's make a copy of that. Paste. Here we go. Right, so here we go. This will fail straight away off the bat. So if I F6 it, it will go wrong. Here we go. And what it's doing, it's trying to find places that don't exist. Yeah. So it's trying to find, like, I think it was here. Let's do that again. F6. What line was it? Line 3077. Let's go 3077. Yeah, it's trying to go to a memory address that doesn't exist because it's contained within a byte array. So that's 20 blah 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 blah, and this happens a lot inside here. We've got branches. Look, we've got a JSR 0800 here, and these branches are going to bad locations, and the problem is we have to find all these arrays, all these data points, and then convert them back into the original bytes here. Now I'm not going to do that here because it's just going to be an absolute nightmare. But I wrote a new program that allows you to take a bin file or PRG file and it converts it into complete and utter memory bytes. Because trying to work out the byte array of this, right? So if we go to 3077, somewhere around it, here we go, here it is. Then you're looking at A1, and then you're typing it in. And I thought, oh god, this is just mind-numbingly boring. So I wrote in my Python infiltrator, there's another program now that takes a bin or PRG and just makes it into a byte array. And I've put the memory location as a comment in there so we know where we are. So then I know where the memory location is, you know, so this one, you've got to be careful because you've got to look to see where the data starts, and that is partly experience and partly knowing what you're looking for. Now normally when a data array comes in, you're looking for either a preceding RTS or jump that jumps away. So as you can see, I'm scrolling up and it's still data because we've got loads of bytes. We've got code that doesn't make sense. Yeah, code that doesn't make sense. So you just keep going, and if you keep seeing labels like this, jam, bad, and all that malarkey, yeah, just keep going. You know, so there's bytes, so this is still data, blah blah blah. Does that, no, this doesn't make sense. You know, that doesn't make sense. Right, okay, we keep going until you get to the point where, no, that's not it. No. I bet you it's an indirect jump. Keep going, jump. Keep going. See, it's an awful lot of data, this is. An awful lot of... Right, this is looking promising. This is looking promising. So that's jumping... Where's that jumping? So that's jumping back. that is jumping forward to here. So it's an it's an indirect jump, look. So that, right, that is, from there, I say that's the end point. So all this from 8C68, and it goes all the way down. And you do the same thing, but this time you're doing it forward. You're looking for code that makes sense. Like here. Alright? So you're looking for code that makes sense. Now I think that starts there. I'm just looking at my notes. In fact, no, it doesn't. And this is one of the things that it fell across. So it does, it ends there, right? But it doesn't end at 9371. No, it doesn't end there. It actually ends at 9370 because 4020 is actually a command, is actually an opcode. So if I look at my byte, my latest build, and look for 9371. So there's the data look. So 9370. That JS, oh, the JSI is right. I must be thinking of another place. There was another place where it said 20 JSR something something, but the actual 20 was part of the array. Yeah, so even though it said JSR and it looked a perfectly good address, it wasn't actually a JSR because the 2 bytes in there was, I think it was LDA something, the equivalent, but the array was doing loads of 20s, 10s, 40s and stuff, and the only way you can find these out is when you compile it and run it, because it doesn't behave. Now, the problem that I had right at the very start with this was these. I mean, I think I showed you on a stream where I had the where it just crashed straight away. Yeah, it didn't get to the menu screen. So let me do a quick search for that. I think it was that. Right, here we go. So this is one of the jumps, and I think there's many of them. There's 2, 3. I mean, this, I think it was this one. Hang on. Oh, it could have been trying to find where it was. Pain. It was jumping to a byte number. I'm trying to remember what the byte number was. Oh, that was it. 9370. 40's RTI, isn't it? Yeah, 40's RTI. So return from interrupt. And what it was doing was, when it's reading, so reading from 3863E, that's here. Well, it's not this one. Hang on, let's see if we can find the one I'm supposed to be looking for. Is it that one? Doesn't look like it. Does that one look like it? No. So where's that one coming? 84C1. Nope. 83. Oh, it's one of these jumps. I think we've got more than that though. Hang on. Let's do this. Ah, the 7. There we go. That's why I couldn't find it. Right, so that's one. No, not that one. Ah, this one. This is the one. This is the one. Where is it? Looking at the byte value. So 9370, that's what I'm looking for. 93, where's that? 4, that's here. No, not in there. Nine 2586. No, it's not that one. No. Oh, hang on, back up. Yeah, I'm just trying to remember where it was. But what was happening, right, was the so it's doing an indirect jump, and here, for like in this case, is the memory array for that indirect jump. Yeah. And what was happening was that in the memory array there was a branch, branch if not equal or something like that. And because it was going to a bad address, because it couldn't resolve the address of the opcode, because the address actually was in the middle of what Infiltrator thought was a 3-byte opcode, it shuffled it back one. So instead of being 9371 that, say, the indirect jumped to, it actually jumped to 9370. Now 9370 had a byte 40, which is an RTI, so it just kept jumping straight back out. So it ran, jumped straight back out, ran, jumped straight back out, and it was purely because of the data array. Like this has got a branch if plus, yeah. It could, so this one's okay because it's got an okay, which means Infiltrator said that this was a valid jump. I'm just trying to, I don't know if I fixed it. Oh, here we go, 7-0, right? And that's what it was doing. It was jumping to an address that was wrong. This is the sort of address that it was looking at. So this is a byte address where the low byte and high byte are grouped independently, and it was 70. And now 70, when it combined with what it was doing, was 9370, and it should have been 9371. And I just, do you know how long it took to find that? How long it took to find that? Even C64 debugger wasn't helping, because as soon as it hit an RTI, that was it. It threw it out. And so I had to step through the program to find out what was happening. And it was in the initialization routine that it was doing it, because it's using these indirect jumps to jump to different areas depending on what state it's in. And I had to follow it. Every JSI I had to put a breakpoint just after it to find out what it was doing, and to understand what was happening. And then I found the JSR that was making it fail. So once I found the JSR that was making it fail, I broke into it to there. Then I stepped into the JSR to see what it did, and then if it had more JSRs in, you do the same thing until I came to a indirect jump. Can't remember which one it was, but it was an indirect jump, and I was thinking, what on earth's wrong? So you look at the values that are coming in, you're looking at the values that are being stored, and it came out with a number, and it was doing an RTI. And then when I looked at the source code, it was purely because of a bad address on a BMI. Yeah? And so even though it compiled, even though it assembled, even though my byte count was exactly the same, so it finished at C002, I think it is. C, D, E, F, 0, 1, 2, 3. There you go. C003. Even though my byte count was exactly the same, it was failing because of the way the assembler had evaluated these addresses, because it's looking at it. Let me see if I can find that bad one again. Not there. There. So it's looking at this, and it's saying that this should be 3085, when in fact it's probably not. This is probably a different number entirely. I mean, where's it going? 8448. So it's going backwards. 8448. So it's going in the middle of there, but it's not actually a branch, it's data. It just turns out to be like that. And so when you compile it, assemble it, you get a different value. And that's why at, like say, at 84C1, so if we go back here and go to 84C1, you'll see that I've converted it into bytes lot. There we go, there's the jump table. Yeah. So this is jump table 2. So I had to find all the different jump tables and make sure that the byte array was correct according to the original. And then I managed to get it working, sort of. Right, so reset that 64. And if you remember the last time I showed you, I had a missing character here. I mean, if you look, I've got a character that's wrong here. So that means there's still some data in there that's been evaluated by a branch or something, and it's just come out as one. The actual value is 1 out, because it's trying to jump to a bad position, which is either gone backwards or forwards, depending on which was closest. And that's what was happening with those jump tables. So the next thing I had to do is then identify all the data, you know, what's data and what's not data. And that's where I am at the moment, because like I say, it's a dead giveaway when you have something like this. That's data, dead giveaway. So you work backwards to find where you've got code that looks right. So this code looks right, yeah, that looks right. This doesn't look right, because one, you've got a byte in there. Now, unless it's a, what was it? Was it set decimal is the one that Infiltrator doesn't do? Then you will, but you won't get bytes like this. You won't get lines like this inside code, right? And then you just go back the other way and try and find the end. Thank you, Mikroman. And then you just, same again. You've got to use your eye. Right here. Looks like we are at a point here. yeah. So here, right, we've got code that looks okay, and it carries on okay, and all the jumps seem to have the word okay. So straight away we've just identified another data array. Yeah, another data array. So if we go to my latest byte dump and do 8A something something, I bet we're in the middle of a data array. There we go. So I worked this out that it goes back to 87EC. Hey matey, how you doing? Right, so this 87EC, so this is here, right, so there we go. That's where I said, right, there's the RTS log, and then I started the data. And this is all data. Yeah, I've been relaxing at the coast. I managed to get back, what was it, 2 hours ago now. And this data means something. And now I think this is either alien data, it's not character set data because it's not big enough. Or it could be a screen setup. But there's another one. And I've had to go through the code to see if I could identify all the areas, yeah, all the areas that are code. So this is the big one, yeah, that goes to 936, 9370. I mean, there's some more. 9489. Here we go. So this is a small section. 9B1A. 9B. There we go. Now if I look at the original code at 9B1A, and you'll see what I mean. 9B, 98. Ooh, too far. There we go. So I said that 9B19 was the last part of the good code, and then it goes all screwed up. So this has got to be data. But hang on a second. Does that look okay? Is that okay? No. Because look at it. I'm ORing the zero value, the zero location. Now that can't happen. You can't do that. You know, this code doesn't really make any sense. Yeah? Even if you come up here and do, right, okay, set interrupt, clear the carry, okay. I'm going to push the status. Yeah, I'm going to push the status, then I'm going to branch. If it's not equal, then I'm going to push the status again. Branch if not equal. Or it with 0 byte, store it in 40. Doesn't make sense. You've got to look at it and say to yourself, does that make any sense? No. This is data. This is not code. Try not to get stuck. What you think is code, try not to fixate on it. It looks like it's okay, but it's not. It's not code. It doesn't make sense, and it's got to make sense. Even though you don't know what it does, it still has to make sense. So we carry on going. So this is where I got up to, I think. 2A, yeah, 9C 2A. Right, so 2A is there. So 9C 2A. Now, here is a place where here's a place that I was talking about earlier, where right here, OOA 20, and then we've got a 2 bytes, 6B, 9C. Okay, right, this is the start of the new code. Are you sure? Are you absolutely sure? And the reason why I say, are you absolutely sure, is can you see what would make me question if that was the start of the next block of code? What's the giveaway? Anybody? The address. Alright then, I'll put you out your misery, right? Look at the jumps above it. Look at the labels above it. Right, look at these labels here. 1, we have 5. Right? We have 5 bad labels going to that one spot. Right? Now, if it was just data, right, and data wouldn't have a jump going to the same place multiple times, right? So here we have got 5 labels, all bad, going to one spot. Now look, it's trying to jump to 9C2A. Yeah? 9C2A. Which is not here. Right? 9C2A is there. So a way of trying to yeah, the way and the way to find out is look for this jump, right? So we're going to look for the jump. So we're here, yeah. So this is 9C2A 95CB bad, right? So there is the jump. So we're going to try and find that jump, yeah. So control find. Right, it's 2 places. So where's the jump? There is the jump. And sure enough, you know, when you look in the original code and you find this bad jump, it's inside some proper code. It's inside some proper code. So that's another tick. Hang on. Even though these jumps are bad because the infiltrator can't reconcile the jump to the position which is there. Now, why can't it reconcile that? Because when it's come through, it's seen byte 0, it's seen this, and it's byte 04. There's no instruction. 04 is not an instruction. Above it, it said 200404. So this is definitely data, yeah? But this is trying to call that. Now, 20 is JSR. JSR 9C6B. Hang on. This is the start of the code. That there looks good. So what I did here is, as you can see, I put that JSR in. So if let me see if I can find it here. See if I can find it. That's one. There we go. So that's where we are in my code. So even though these are infiltrator class them as bad jumps, they are legitimate jumps. They were just jump because of the assembler. The assembler was saying this point is the new point, not this. So when you run it, blew up. Just, you know, it's not a command. 01, 01, 20, okay? And then it comes and it tries to execute that. Bang. So that is another marker about how to determine the difference between data and true code. If you have many jumps going to the same point, inside what you think is data, check where it's trying to jump to. Like here, 9C2A. Right, so this is 9C229, which is 01. So 9C2A is this. What would this be if I tried to disassemble that? Well, that's JSR 9C6B. Is that a legitimate address in your code? In this case, yes it is. So I converted it to that, kept these bad labels in because they're used, and that's the start of our next chunk of code. So all this has been remmed out because I have now put this in. So this is where I've got to, yeah? So I'm going to run this when I finish this. And we'll get rid of all that because we don't need it now. Because that is pure data, and that's all. Pure data. Right, F6. So, we're not finished, by the way. This is just... Right. So, we know we've got a problem here. So, it may be data that I've not identified yet and done the copy of the data array across. I've also got to think this is not quite right here. But F5 works. Yep. F3 works just from 1 to 2 players. Right, let's see if we can start it. See what it looks like. Right, I'm going to pause it there. I think that paused it, didn't it? How do I pause it? I've forgotten how to pause. How do I pause it? Oh, which version of... I don't know if I'm running the right version of Vice. Pause, pause, pause. Oh, there. Alt, pause. There we go. Right. So even though... Thanks, Mikroman. Even though we have got a working game, yeah, all the graphics seem to be in the right place, we still have issues, like here. We've got issues. And... yeah. So the data, I'm still assembling data. I'm still assembling data that is that's assembling it wrong. You know, is that one character out? And then the only way to look is to look at the character set. But it's working. The whole thing is fired up, and that's because I've identified where the data's I mean, the jump tables were were incredibly important to find. You know, once you look for this, yeah, and you look for it, right? There's a jump table. So you look at the code above it, right? Where am I getting the value to do this jump? So 98EB, so that's here, yeah. 98E9, so that's directly next to it. So basically, these jumps are being held in pairs, yeah. There was another one that was not being held in pairs. Oh, that's being held in pairs. Is that being held in pairs? Yes, it is. And that one. But one of them, this, I think it was this one. It's not being held in pairs. So it was getting, yeah, this is not being held in pairs, look. Right, so this jump was getting from 2 different areas. So it's getting the low byte from one area and the high byte from another area. So these are things that you've got to think of. So I've just done this bit. So the next thing is to find the next set of data. So we just have to look and see. So I've done that. Right, okay, so that's me done that. So I can get rid of that lot. So that's, I think that's data. Yeah. So just have to keep looking and see if we can work it. Yeah, it's interesting that their control systems are being done by indirect jumps. You know, so, but I think that's a similar sort of thing as I did in Lunar Lander, when the game flow module was controlled by an indirect jump from a jump table. And I think C64 Marks did his Neptune lander doing that as well, Elite. So we'll see if we can find some more data. Now this is a dead giveaway, look. So I think at 9E something something, we're going to come across some more data. So this is 9D. We've got a CLI and then a jump. You know, code still looks good. Code still looks... Aha. Now this doesn't look right. So that looks okay. But the problem here is we've got this. And then we're doing a branch. But where's that going? Is that going backwards? Where's that branch going? (9E12). Yeah, exactly. It doesn't look right. 9E12. So that's coming up here. So that's coming up here, look. But I don't think this branch is legit, because if it's not equal, it can't do this. This doesn't look right. And you know, even though my gut is saying that might be okay, let's see if we can find it. Let's find it in my assembled. There we go. So that's our code. So that's the problem so let's see if we can find where the jump is. So it's this. I mean, it looks okay, but it doesn't make sense. Load CODE. Yeah, CODE. Let's see if we can find any instances of that location. Right, so that works. Okay. So, branch if not equal. That goes. So, are they saying, right, this is what you have to think to yourself. Are they saying that it will never store a 0 value? This location would never store a 0 value. Yeah. It's exactly. But you've got to remember, Andy, that this is a cartridge game, so there's no such thing as self-modifying code in this code. It can't do it, right? I think it's just a fluke that happens to be a legitimate... Oh, code joke. Yeah, I know. It's just a fluke that is actually a proper address, code. So this now makes me think that, okay, this line here, up to that line there, is a legitimate code. You know, that the fact that they know that what they read from here and what they store from there will never be 0. Yeah? Because if it was 0, it wouldn't do this jump. It just carry on into this blah code. So we need to work out what that is. So that's 9E6E. And now we need to find where the data ends and the code come back. So I'm going to look at it and scan through it slowly so you can see. And I'll stop where I think it's legitimate code. In fact, I think that's it. I think that's the end of the code block. So we are going to get rid of all this lot, because I don't think any of this is legitimate code. There's plenty of branches that could be wrong. Oh, thank you, mate. Thank you very much. Yeah, like there. There's a branch that goes bad. So that means it couldn't rectify the position it was trying to go to. So I think that all this is just data, because after that it's just data. Yeah, just data, blah blah blah, just data all the way down. So we need to go to 9E6E. Oh, there's data. Yeah, that's what we're aiming for, isn't it? So here is where we are going to. We're going to rem out until we hit there. Right, so I need to look at where that byte starts. So we are looking for 9FFB to 9FFB. To be honest, I think we should go all the way to the end. Let's have a look. Where do we stop at? We stop at BFF0. 0, 1, 2. So that's the last byte is 8A00. Yeah, I think we should go all the way to the end. So let's find our starting point, 9E6E. Nine E6E. Oh, mate. Bombing this stream again, are we? So 9E6E, so that's there. So we are saying 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E. And that looks about right. 02. I think that's where it started, wasn't it? Yeah, byte 02. So we are going to copy from there all the way down to the bottom. So we're going to copy that, go to our code over here, and we are going to paste it in into there. There. Right. Now all the addresses are there, yeah? So we just need to go .byte like that. So all the addresses are there. And what I've done with this program, it creates lines of 16 bytes. So the addresses are always going up in tens, hex 10. And we will get rid of this lot because we don't need it now. Right. So we should be able to F6 this and it still work how it used to be. Right, so control reset. Oh look, our player is proper now. So one of those branches was causing this to be one character out, and this that's the same, wasn't it? Even though it looked funny. Right. Okay, F1. Let's see if... So we still got a problem here. That means I've still missed some code somewhere. Well, not code, some data. So even though I've done all of this, I'm still got data in this code that I have not recognized. So we have to go through it again and again until you get it right. Now the problem is, because we don't know where we don't know where the character set is, and the only way to do that is to look at the code and try and work it out. You know, DO16, DO18. I think they're the two fellas, aren't they? Have I just hit the thingy on the head? Let's have a look. Hardware VIC addressing system. Right, so we are looking for DO18. Where is it? Oh, it's there. 18. So we're storing 18 in DO18. Right. So 1 is on this side, so 8. That's there. So it's alright, so it's saying that the character set is from 3800. Now 3800 is relative, remember? So we've got to find the bank. So that's 8. No, it ain't. That's not 8. No, that's not 8. That's 8. There. 18. 18. In fact, that's not 8. That's it. John, get a grip. Get a grip, mate. Get a grip. So, relative 2000. So we need to find out which VIC bank we're in. So DD00. So here we are, DD00. Let's go back to that. 6. 4, 2. 4, so that's 6. So it's not that one. So it's got to be this one. It's got to be this one. But that wouldn't make sense. That wouldn't make sense. Because the cartridge is from 8000 onwards. So I would expect it to be 01. Let's see if we can identify this. Right, Shift F6. See if we can identify where the right. So Control Reset. Right, so we are.
Hello, John here. Thank you for following. Hope you enjoy the stream.
Thank you for following. So that's where the screen is. So that's in the 4 area. All right. Because there's no other screen with that on it. Right, so the cartridge is here, yeah? 8000 up to here. But the screen is there. So the screen is definitely... I mean, it's flickering, but it's definitely there. Where's the character set then? Show me where the character set is. Where's the character set? Well, there's DigDug at 6,000. I wonder. Hang on. F1. Let's run it. Ah. It still says the screen's at 6,000, doesn't it? Oh, it's a bitmap. Oh, it's a bitmap. It's actually working in bitmap mode. Look. Oh, I can't get the joystick working. Right, so there's no characters. Down here we have got a dodgy value. That is doing, that's switching, isn't it? Switching screens. Right, there we go. Ah! I'm painting. Don't want to paint. I don't want to paint. I want to move that. Oh, I can't move that. Right. So the character set is only on the first screen. Okay. So the character set is only on the first screen. So this is actually a bitmap. A bitmap game. Ooh, that makes this interesting. Definitely makes it interesting. I didn't know that. So we definitely have our screen at we definitely have our screen there, in there. So that means 4,000 means that the character set, it must be at 6,000 because this is the offset. Yeah. So D016. What's 6? I can't remember what 6 was. Oh, that's bitmap mode, isn't it? Right, the top bit is fixed, the screen setting, so it's 1. So 1.8, yeah. Okay. Right. So we know that it must be copying the character set. That's probably why there's that pause right at the very start. There must be, so there's in here there's a routine that copies the character set. So just need to find it. Just need to find it. Shift F6. No, I don't want that. I want... There we go, that's what I want. Control reset. Where is it going to set it? So screen's at 400. And the character set is flickering between 2. Right. So DigDug is at 6,000. So there must be a raster going on here. And then it changes to that, which is the normal character set, which is at 5,000. Right. So that's why we've got OK characters there, but that's DigDug. So DigDug is at 6,000. So we just need to figure out how DigDug got there. How did DigDug get to 6,000? And then we can work out where the character set is. Okay, right, let's click on here, press F1. So that's definitely all bitmap, even down to here. Yep. And that's multiplexing, isn't it? Is that multiplexing? One, two, three, 4, 5, 6, 7. Yeah, that's multiplexing. So we've got a multiplexer going on as well. Right, so we've so this is a bitmap game and it's got a multiplexer in it. Docster. You're gonna have fun doing this, mate. If you're on. So to recap, yeah. First, when you've converted your so when you've infiltrated it and you've converted it into kick and you've done your first try to assemble, right? The first thing you need to remember, so let's see let's create a file here. So the first thing you need to remember is fix all illegal jumps. And what I mean by that is in the data there will be a jump to a place that doesn't exist, yeah? And there would have been a label created that doesn't exist. So you have to go to the original infiltrator document, find where that jump is and just convert it into bytes, so 20 blah blah blah, because it will never, infiltrator will never get there. See, I've got jumps in here that go that jumped before 8,000, yeah, but we didn't disassemble before 8,000 because the game had been moved to 8,000. So those jumps do not exist. They're in the middle of data. So that means you've got to then, every time you hit it and you find another illegal jump or the label doesn't exist, convert it into a byte array, carry on, carry on, carry on. Next thing you need to do, 2, fix all 0-page errors. And what I mean by this is like here. You're doing, once you've got it to run.
Ladies and gentlemen, 6502 Kebab has entered the chat.
Hey mate, welcome. So the next thing you need to do when you've done some infiltrating disassembly is fix all the 0-page, because if that was still like this, which it is in the code. I mean, this is right at the very start, so we should be able to find it. So this is the original. Do. There it is. There it is. Kick will optimize that to become store in FA. Right? And that is wrong. Yeah? Because when you do your byte compare, how many bytes you've assembled compared to how many bytes you disassembled, they will be out. And I think in DigDug it was like 26 bytes short. And that's because there's 26 references to 0-page using a word, not a byte. And you have to do this sort of thing. So that's store absolute. Yeah? And the way to find it, as I found out, is to do this. So you just do find, and you basically go, put a space in, $, 0, 0, and then find all the zeros. Right. There's nothing there. Find all the ones. Nothing. Find all the 2s. No. 3s. 4s. 5. 6. 7. 8. 9. A. B, C, D. Come on, pick me one out. Is it done it in that search? Let's do that again. 1. There's none in there. 2. Let's take the space out. Here we go. That's better. 3. 4. 5. And basically what you're doing, you're trying to find all the... I thought I did. Nine. A, B, C, D, E, F. There should be more than that. There should be a lot more than that. There was loads. No, I put 0 in. That's 0. 0. There should be more than that. It's just found one, but there's loads. Oh! I know why. I know why. I know why. Let me do it in here so I can show you. Let me do it in here. So, like I say, space $, 1, 2, then start with 0. There you go. So there's 3 there. So you've got to change though that to be the equivalent. So here it's, I think it's ABX, absolute by X. This one is absolute, you know, dot ABS, and then you do 1. There's 1, so OIR, and I think that's ABY or ASY or something like that. 2. There's nothing of 2s, 3s, 4s, 5s. There's 3 of those. 6s. None of those. 7s. No. 8, 9. A. There's 1 of those. B. 2 of those. C. 1 of those. D. E. and one of those. But because I've converted all those errors that you spotted, all those errors that came up, only came up because they were in data. They were in data. And so when the assembler assembles it, it always optimizes. So if you've got 0001, it will always optimize whatever the instruction is to be a 0-page addressing mode instruction. So you then have to tell the assembler this is not. Like here, this is not a 0-page instruction. This is actually an absolute value instruction. And so you have to do .abs, and they're all listed in the kick documentation. So if you go into kick and you type and you go into 0-page, I think it's that, assembler directives. No. Where is it? Here we go. There it is. So for ABS, right, absolute is ABS. There it is. Or ABSX or ABSY. You have to tell it what it is. Because if you don't tell the assembler what it is, it will always optimize. So 00FA will always be store FA, not store 00FA. You've got to tell it what it is. And they're all different. So what you do, dot, ABS, that's absolute, yeah? And they're all listed in the documentation. So that's point 2. Yeah? Point 2. 3. Find all look jump tables. Now, the way to do that, I found, is just basically just doing find again. So you go jump, $, and then that's it. And as you can see, we've got 7. Yeah? Find all the jump tables. Now that's a legitimate one. That one is. That one is. That one isn't. That's in the middle of data. Look around it. It's just nonsense. That one is in legitimate code because this, if you look at this jump, that's here. So it's jump in there and then does it. That's legit. That isn't. So once you've identified the jumps, then try and find where it's setting the value. So 9A. And here you are. Here's the address of your jump table. Yep. Which 235 is here. There. So 234, 235. So that they're doing words. They're pairing up. So that is your jump table there. Because this looks like proper code. So these are pairs. So you've got 1, 2, 3, 4. So there's 4 pairs there. And you do it for the, like here. So 84C1, which is here. And you just work out the jump table. Now this looks like legitimate code there. Down. So 2, 4, 6, 7, 8. And remember, on a jump table, there'll be no label. No label whatsoever. So even though this is a jump table for data, eventually you're going to have to convert them into labels. You're going to have to find the jump points, create a label, and then done it. I haven't done that in this thing yet because I haven't got that far. But what I have done is named where the jump locations are. So if I do a find jump table, there you go, there's 9 of them. So there's jump table 1, jump table 2, jump table 3, and there's the reference to a jump table 3, jump table 1. So we're back to 1 again. 2, 3. There you go. But as you can see, they're still hardwired into the absolute position. Yeah, I've not created these into labels yet because you need to go back to find where they are. So we could do it here. Let's do it. So it's low byte, high byte. So we're looking for 8599. So 8599, which will be down here. 859898. So this is 8599 here. So we could do jump table 1 1. Yeah. Copy that. Go back to the jump table. Here we go. So here we'd do dot byte less than that, comma, greater than that. And that should be the values, alright? And you'd have to do that for all your jump tables. So when you've identified all the jump tables, go to where they are, have a look, see if you can find it. Like here, it's 8525. So that's pretty close. 8525. 8525. So this is 85. No, that's 82. 8525. 8525. 84. 8524. So that's here. 852425. That's here. So that's row 2. So we'll go back to where we need to be. Jump table 1. And this one. And run that out. And keep checking. Right, so we're going to compile it. We're not going to run it because we want to look at the bytes. Yeah. So we're looking at 8227. So look at the dump, the byte dump, 8227. There we go. So we should still have the same values in there. So 9985, 2585. Okay, so what was it? 9985, 2585. See? Yeah. Yeah. Okay, we'll do what Andy says there. So he's talking about doing that. But you've got to remember, one of the jumps is not paired together. They are separate, yeah? One of the jump tables. Thank you. Yeah? So, in this particular jump table, they are paired together. But there was one that wasn't paired together. So be wary, because you would have to do it this way for that. Yeah, yeah, you can have... You can There you go. And to be honest, I've got to do this anyway. For giving me the instructions on how to pause in Vice. So, that's the next thing you've got to look for. Any indirect jumps in the code, and then find their relative tables to be able to do this on. Yeah? So 8785. Might as well finish this one off. How many... That's just because you've been watching, innit? I think the gambling's work. I think the gambling works, but you might lose it all. Right. So this one's 87 AF. 87 AF. We might as well do the rest of them. 87 AF. Oh look, we've actually got references to it, but we'll add it. So this is row 3. Then we'll go back. Rem that out. Dot word. Three, and might as well do the last one. So that's 86 E1. 86 E1. Oh look. Even that had labels, but we'll make his own. Lost where I've gone now. Jump 2, jump 1. Here we go. It's the much acclaimed I'm after. Alright. Just wondering where the code for this game came from. I have a cart version that seems a little different. Really? I've written a converter from kick to beeb and back again. I'm testing. While I was on the coast, sunning myself with my laptop on my lap on the beach. So I've written a converter to convert from. I've written a converter to convert kick ASM into beeb assembler ASM and vice versa. It only does the basic stuff. No, it doesn't do all the clever 4 necks and everything in kick. But it converts, say this. Say if this program, if I wanted to convert it to beeb ASM, I could run it through my converter and it will spit out a beeb ASM version of this code. Yeah. So we need encoding fixed and the DFS writer. Yeah, but the DFS writer, I've already got the code for that. I can write a DFS writer. Yes. Because I was trying to, you know, the beeb MMB file. I've got that editor that I showed you. I've actually got the source code for it, and I was converting it. I was trying to convert it into. I'm trying to convert it. Let's just say that I'm trying to convert it into Node, so we can have a Node version of it, so it would work on any platform. Mate, what are you doing? You come visiting? Okay. Say hello to everyone. Gimme, gimme, gimme. I will do when I've. Yeah, I will. I'll see. Yes, mate. I'm here. But yes, I've got the source code. I've got the source code for the DFS viewer and the beeb MMC file, MMB file, sorry, editor. So, you know, remember when I ran this? Hang on, let's get it in here. This, I've got the source code for this. Yeah? Right, so I've got the source code for this, and this then, in this program, if you double it a file, it fires up the DFS image reader. So I've got the source code to read the image, so should be able to write an image, should be able to do an image. I mean, can I do file new? Yeah, well, file new single-sided, file new double-sided image. So there you go. And I've got the source code for that program. So yeah, I was going to try and make a node version so it'd work on any. It's the directory structure and the addressing on it that has me. Well, yeah. I mean, I've got the like I say, I've got the code. Hang on. See if it's where I think it is. Let's just have a quick look. You built it in C. Yeah, well, I don't build things in C. Just trying to find it somewhere around here. Where would it be? Where would it be? I have too many directories. Too many directories. Oh, it'd be on my VM. It'd be on my development VM. I haven't touched C since I did my degree, mate. Which was well, I finished it in 1997, so I haven't touched C since. I can read C++. I presume that that's because I coded in C, but bits of it stuck. So, yeah. Is that it? No, that's not it. It must be on my VM. It must be on my VM. I'd have to fire it up with the original code on it, because I don't. Oh, hang on. Oh, there it is. There it is. Whoop, there it is. That's the old one. That's the old one. DFS imager. Right, so this is it. So disk table op. I bet that's what you need. Let's have a look. Open with. I'll do it in there. So the program itself, as you can see, was written by this dude, and it's in VB6. And so there is that's the disk entry, disk table entry. There, and then we've got read table. Okay, that's the disk table. Okay, so we're not wanting that. We are wanting the file, so it must be that one. Must be that one then. There we go. Catalog file structure. Name, directory locked, sectors used. To catalog. Oh, that's a catalog entry. That's the file entry. So yeah, we've got the code to make the files. But I haven't got VB6 on here, I don't think. No, I haven't. I have got it on a VM. And I think that's why I was saying it's on the VM, the new code. Because I was trying to convert it. I can't spell cookie without it. Oh, what's going on Discord? Oh, right, okay. Okay. I know, and that's why I was trying to convert it. I was trying to convert... What I was trying to do is I was trying to convert... Originally, I was trying to convert it into .NET Core. And so it would be like the git commands, you know, where you would say... you would run the command in a directory where the MMB file is, yeah? And then you would run it. So you could say dcat, and it would list all the disks in it, and then you could do demount or something that would tell the system that you want to look at that one, and then it would allow you to create a file, create a disk, or create a file in there or something like that. That's what I was trying to do. I was trying to make it so it was in .NET, so it was just commands, you know. But then I thought, no, I can write this in Node. Surely I can write this in Node and make it that a fully feature-rich thing. So that's what I'm trying to do. But I'm trying to get the character editor done first. That's my first thing, and I don't want to be jumping around on project after project, or I'll never get anything done. So yeah. Right, back to this. So remember, identify your jump tables. Jump tables will not have labels, so you have to create those labels and then then convert the original into your jump table. So this is where the jumps are paired up. Yeah. Are you sure that would work, Andy? Oh yeah, we did. Hang on, let me build it. Let me build it. Gotta find it. Oh, let you off. Now, the other jump. So we have another jump that is not paired. Yeah? So that's paired. Jump table 3, that's paired. And there's another one. There's another jump, and I've lost it. Hang on.
Oi, John, pay attention to chat.
Oh dear. Okay. How many have you got anyway? There you go, for doubting you. 96. Jeez. Right, let's find that other jump. There. That's where it is. 8C65. Ooh. Have I converted that to bytes? 8C65. Right, so that's the jump table there. Ah, there it is. That's because I haven't marked it as a jump. So these here, so this is here, are now paired. So we are looking for 8C84. So let's have a look in here. 8C84 and 8C7D. 8C84. So there we go. We're looking for a load of 93s, look. Yeah? So we're looking for a load of 93s in here. That will be this lot here. And then 8C. So that's the high, and then 8C7D. So that's going to be the back end. So that's going to be these here. F, E, D, yeah. So it's going to be those. And those. So that's... How many have you earned? So, you've got to remember that in this jump here, they are not paired. Right, so you'd have to do the greater than, less than sign. And just because I've got it now, I am going to do this. I'm going to do that, comma, get rid of that, and then the 93s will be there. So we have got 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Bang on, we are in sync. Right, so we'll just separate that out. And then we will do this. So this is jump table. Jump table 4, isn't it? 2, 3. Yeah. Oh, hang on. 3. Yeah. Jump table 4. See, there's one there. I didn't look. There's one there, and I missed it. I haven't even labelled that one up. There we go. So this is jump table 4. So jump table 4 low and jump table 4 high. And of course we don't know what they're doing, so we'll just leave them as jump tables. And that is the low one, comma Y, and that's the high one. Oh, how dare you do that, VS Code. Right, so that's point 3. Identify your, I mean, like saying I've missed one. There's one there still. Identify your jump tables and label them appropriately. Yeah, to make sure that when you start optimizing. Oh, did I miss the Y off? Yes, I did. Thank you. Ooh, good way.
Oi, John, pay attention to chat.
I knew what you meant by commercial Y. I knew. Just give yourself some points. No, I better give you some points. You'll be adding yourself hundreds. There you go. Alright. Link the I'm still trying to work that out. I'm still trying to work that out with the bot. Right. So find all your jump tables. Label all the elements in the jump tables appropriately, because when you come to getting rid of all the space and the inconsistencies and start working out where the character set is and all that and doing, you don't want to lose those vectors. Yeah. 4. You do this, mate. You go like this. That's how you do it. Just type in hello. Like that. Right. So once you've identified the jump tables and all that, next thing is to identify the data areas. And that's the tricky one, because that identifying the data areas, like I've showed you here, is you've got to look at what you're seeing and saying to yourself, does that make sense? Yeah? Does that make sense? So identifying the cutoff point between what's data, or here, what's data, and then what's not data. Sorry, what's code and what's not code. That takes a little bit of experience, but common sense. Common sense. If you've got code that's got BYT and multiple BYTs in it, bytes in it like this, then it's not code. It's data. It's just the disassembler's tried its best to say it's code, but then couldn't do it. And also look for things like this. Labels with the word jam or bad in. I mean, where's a bad one? Jam. There we go, bad. And the reason this one's bad is because it's trying to call 8CEF, but the disassembler says the next best instruction is at 8CEE. It's one out. Alright, so any label that goes to that will be 1 byte out. So that's another indicator. Look, because surely you shouldn't be doing that in code. Yeah? Be mindful about what you're looking at. Look at it. Try just say to yourself, does it make sense? It doesn't need. You don't need to know what it's doing, but does it make sense? TAX TAY doesn't make sense, especially when you do that behind it. And that's what I'm saying. It takes a little bit of experience to do that, but as long as you've got a little bit of common sense, you're all good enough to code in 6502. You're all good enough to do it, because I've seen some of the assembly files coming my way asking for help. You all know how to do it. Yeah, you all know what good code looks like. You don't have to understand it to recognize what is good what is code and what is not. Yeah. Because if you didn't know what is good code and what is not, you wouldn't be able to code it. Yeah? It's like this. This does not make any sort of sense whatsoever. This. Is that proper code? Right, I'm EOing with F0, X, rolling with 56, X, then I'm branching if the overflow's set. Really? No. Doesn't make sense. Am I thinking the right person? I'm probably thinking they're of the right person as well. Yeah. I think I know who you mean. Anyway, so this is just... I'm just trying to help you. So, dead giveaways, bad labels or jam labels, straight away. Dead giveaways. They will tell you... I wasn't going to mention any names. Right, jams and bads are dead giveaways for data. The trick is to identify where the cutoff is between code, data, and then back from data to code. Yeah, and that can be tricky because, as I showed you not long ago, where the data actually stopped halfway through, but the assembler thought it was an instruction. Yeah, but the dead giveaway was those labels in front of it. Yeah, we had 5 of them all in one go. Let's see if I can find it again. It was somewhere around here, wasn't it? It was later on. I can't remember where it was. Oh, it was 9370, wasn't it? No, that was the jump. Okay. I'm looking for bads. Can't find them. I don't know where they were. Forgot where they were. Okay. It was just a bunch of bads together, wasn't it? Here we go. I mean, this is a prime example. I better look at that in mine. Don't remember that. 9936. 9936. Oh, I did work it out. Right, because this is like, here we go. This is another incident of data here. So this is data. It's only a small set, but it's data. Data here encroaches onto the disassemble. So the assembler has tried to link to 9936, which is this byte here, but couldn't. But we have many of them, yeah. And so what I've done is I've put it in the right place. The byte 06, which is there, I've put into this data, and I haven't converted these into bytes yet. But then it was A5 3B. Now A5 is load A with 3B, and that's how you work out where the boundary is. If you see something like this, this is a good indication that this is where the code starts. But that is not the instruction you want. It's that one. And the other one is, if the code looks sensible, you know, like here. So this is data. Right, load Y with D off it. Load, okay. Return. Okay, that looks reasonable. Where's that going? Is that going forward or backwards? 98. Oh, it's going backwards. 98 D1. There. Yep, that's okay. And then it does RTS, and then we've got data. So this is data here, plus that 06, and that's why I've put it there, but I haven't transferred it into data yet. So that's point 4. I identified your data areas. Point 5. Check after assembling byte size of PRG to original. make sure your program's the same size. Make sure that your original, let's say it was 26 bytes, you assemble yours, because you're supposed to be reverse engineering it, not changing it, just reverse engineering it so it works, right? If it was 26 bytes that you disassembled and you assembled and it's 24, there's something wrong. Yeah? You missed something. Always make sure that your byte sizes are the same. Yeah? 6. Locate character set. The only reason I say that is because then once you've located the memory of the character set, you can then run it through my scripts that make proper kick assembly files out of the character set. Yeah. Same with locating the sprite data. So I need to locate the sprite data in this program because it's multiplexing the sprites on the bitmap. Identify the sprite data, run it through my converter that then converts into assembly script, and it converts it in a fashion that you can look at it, you can see what it is, you can see the numbers, and you can see what the sprite is. Then hopefully after you've done all that, you should have a program that works like we have here. Now I haven't identified the character set yet because we haven't gone that far, nor we haven't identified the sprite set, but there we go. So we've got DigDug running. I don't know how to play this silly game. Hey Aquafin, yes, I know about the round one. We've I've got some bad, dodgy data, and I think I've probably still got a branch in the middle. I haven't identified all the data. Like here, look, this is data, and this is all data that I need to, because this branch could be evaluating it wrong and creating a wrong data, so I've still got to identify all the data points in it. Yeah, it's dodgy. This is data. So from that point, from this point onwards, this is data. In fact, while I'm here, let's look at it. So we're looking for 98D7. So let's find it on here. 98D7. 98D7. 0, 1, 2, 3, 4, 5, 6, 7. That's LDA. So we're looking for a 60, which is a return, isn't it? So 60's there. So that's where we're starting at. Byte 82. That's our start point. And our end point is 991D. So 991D. So we're looking for, so DOF, that's there, so that's there. So that's our data. Grab that. Dot byte. Paste that in. So paste it in. Now we'll see if we are right, because dump, let's see, where are we? 991D. Let's have a look. 991D. So let's just find out what it looks like. So 991D, so the very last byte is 24, and then 1D is AFOD. So if I hit that, get rid of that, and then look back here. So 991D should be, yes it is, and our RTS, so 991D is what was expecting. That looks right. That looks right. Because we had an RTS in there somewhere. Yeah, by 82 RTS. So that's by 82 RTS. So that's data that we've now corrected. See? Live on stream. So there must be still some other data in there. Let's see if has that fixed anything? Right. See. Has that fixed anything? Well, it hasn't fixed the round. So there must be still some data in there that I haven't identified that I should. See, let's just do a quick scan. If you see any dodgy data, give us a shout. Dodgy code, not dodgy data, but dodgy code. Because that's where the data will be. No, that looks alright. That's bytes. Dodgy code, dodgy code. Come on. So that's the jump table for that. I mean, this is data. In fact, all of that's data, I reckon. Because there's no jump, unless this is jumping here. But this is data here. Let's just do that. But we're looking for what we think is data, but with branches in and stuff like that. Because that can affect what it looks like. Right, so this is where I started finding the data that I think it is. So that jump's okay. Let's see, where are we looking at? 8 BBF. 8 BBF. 8 BBF. Hey. Hello. Oh, Mr. WauloK. Hello. So 8 BBF. So that's 8 BBD, which is this instruction here. And then we've got the jump. And then we've got 0, 8A, 56, 0, 22, 5A, 0, 55, 15, 0, 0, 5.
Hello,
So that,
John here. Thank you for following. Hope you enjoy the stream.
oh, thank you for following. Whoever that was, I didn't quite catch it. But thank you very much for following. Right, so this is data, but it's correct, so I haven't got that wrong. So we'll carry on, and we'll see if we can find some more data. Nudfavida. Nudfavida. That's a cool name. I can't say it. Right, so we've got some more data here. This must be 9BOC. 9BOC, no, 8C12, that's it. That's here, 8C12 here. So that's the jump, and then we've got 01, 02, 34, 68, A. So it's just checking that the data's the same. Oh, hang on. Whoa, 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 whoa. Missing a dollar sign. Am I missing a dollar sign somewhere else? I am. There. And there. Right, I wonder if that's fixed it. Because that would be wrong. No! Well, it's fixed something. Okay, I need to check my data statements that I've hand typed in to make sure there's dollars. I mean, that's still out of sync, isn't it? Oh, it's there. Let's see. I doubt it, but no. I've still... That's me. I've hand typed that in and forgot to put the dollar signs in. Now it looks right. Now we know this is what I copied. So we know that's okay. Any more data?
Ladies and gentlemen, 6502 Kebab has entered the chat.
No, he hasn't. He's already here. Oh, I didn't do my announcement, did I? The ones I've been playing with. Oh, I've got to do that. I've got to do that. Where are they? I've got to embed them in. I need to embed them in. Let's see. That one.
Hello, and welcome to another Old School Coder stream. I now introduce the man who mastered his craft as a young boy, the one and only, top WauloK, Old School Coder.
Get in there. I've got to do my introductions properly. Right. Here's some more data. And we've got a bad. Oh, here we go. Here we go. That would be one out. 96B6. Have I got that written down? No, I haven't. 96B6. So that's going 1 byte too early. But this is where it stops there. So we are looking for 9693. Okay, 9693. And it ends there. 96DO. Right, let's find that in our memory. 9693. So 0, 1, 2, 3. So we're copying there to 96DO. Is that where we're copying to? 96DO? Yeah. 96DO. To there. So copy that. And we are replacing that. Get rid of that, get rid of that, get rid of that, get rid of that. Right, so assemble it. Okay, no errors. Look in here, so 9693. Let's just make sure it's still right. 9693. Starts with
Hello, John here. Thank you for following. Hope you enjoy the stream.
N for Bumbu. Thank you for following. Thank you. Hope you're enjoying it. Right, so 7A is the start, 0 is the end, and our last number was D96DO, 96D1. Excellent. So our probably a bot. Okay, so let's fire it and see if that may have been our problem, because that did have a branch to a place it didn't like. Come on. Oh, as the crowd goes wild. Ooh, ooh, ooh. There you go. So if you remember, this one here, this when the assembler assembled this, because it was a byte out, it got the wrong value, and so I reckon this in here is the text to make that round, and I put money it's that. Put money, it's that those two, but that byte there. Let's have a look. So BMI bad, which is there, that one there. So that would be, should be 07, and I bet it was something else. All right. And so that, when you assembled it, would have been a byte short, so that would have been 6. That would have come out as 6, and that's why that round wasn't working. But that's it. If Docster's around, there we go. We've successfully reverse engineered DigDug in Kick, and it works. And everything looks okay. Oh, it got me through the wall. That's not right. Oh, come on. Leave me alone. Run! Leg it, leg it, leg it, leg it, leg it! Ah! Right, there we go. So that is... So here these are the steps that you have to go through once you've disassembled in Infiltrator, and then you've taken right. So this is what comes out of Infiltrator. Yeah, this here. This is what comes out of Infiltrator. Then run it through my converter to convert Infiltrator disassembly text into kick assembler, yeah, and so you end up with something like this, yeah. Then, as I've put, oh come here, give me the thingy. That's it. Fix all the illegal jumps. Infiltrator converter. Fix all the illegal jumps. So all the jumps that go to parts of the memory that you didn't copy from Infiltrator, yeah, you're gonna have to convert them back into bytes, yeah. Fix all the 0-page errors. So that's where the assembler has looked at the instruction like STA$00FA, it's optimized it to STA$FA. Find all those 0-page errors and correct them using the kick abbreviations to make them proper. Find any jump tables. Find the jump tables. Make sure that the jump tables are correct, because if there's a branch in there going to a bad, as we've just spotted, it will change the value because it's jumping a byte further away or a byte closer to where it is and not the one. Identify all the data areas. Once you've identified all the data areas, convert them into byte areas like this. Convert them into byte areas. I've written a program to do that. I should say not a program. I've written a Python script to take your PRG and create a byte array that you can just copy and paste in. That's what this is. This is the byte array of DigDug 8000. Once you've identified all your data areas, make sure they're typed in right if you've done them by hand, like I've just shown, where we got 4 values without a $sign on it. Always check that what you build, so here, what I build, is the same size as what I disassembled. Now, here ends in 0. Yeah. Here ends in 0. BFF0. beat FF0. I have got the same number of bytes. Try and locate a character set if you've got it, because if you can locate the character set and the start address and the end address, then you can go into Vice, save that memory as a separate file, then use the Python script, convert it into a character set assembly file. Yeah. Same with the sprite data. If you can load the sprite data, if you know where the sprite data is, and locate the start and the end points, save it as a bin file. Use my Python script to convert it into kick assembly text. Also, for those guys that are CPS users, I've got scripts to do that in CPS as well. So there are pairs of scripts, one for kick, one for CPS, one for kick, one for CPS. And if you don't know what CPS is, that's CBM Program Studio. And that, after you've done all those and checked that everything looks okay, you would have... There's a beta in my Discord, WauloK. Beta 8 was released today for testing. Apparently there's I haven't downloaded it yet because I only got back from holiday, what, 4 hours ago. So there's beta 8, it's in Discord. Oh, you've added it to the Patreon page. Okay, yeah. And so let me just, I'll show you the, oh, I can show you anyway, can't I? Whoops, didn't want to do that. So there you are, old school coder. Now it says infiltrator to kit converter, but I've got the CPS ones in there. So this is convert infiltrator file to CPS assembly, convert SBR file, that's kick, this is CPS version, there's the character set, and I've just created another one that I've used which takes a PRG and just creates a byte array out of it. So you can, once you've done the infiltrator, you can use either kick or CPS if you want to tackle one yourself. So and all it does, it just takes the raw infiltrator disassembly and reconstitutes it into the format that you are familiar with. So you can just load it, just add it straight for CPS, add it to your project. For kick, you can just assemble it off the bat. But like I say, you have to do these 7 steps, and you know you don't have to understand how the program works. I have no idea how DigDug works yet. Yeah, we have just disassembled it and reverse engineered it to a point that we can assemble it and it run correctly. Yeah, so we don't know how it works yet. We just know that we can now press F6 for kick or F5 in CBM and it runs, yeah, without any errors that we can see. So we got rid of all the text errors, and we got rid of the funny text on the first screen. All right, and we already know. Oh, pause. We already know that this is multiplexing sprites, because when we looked at it in C64 debugger, we noticed that with certain sprites at the top disappeared, as like for when the Dragonfire came out. So we know there's multiplexing going on, but it's not intensive multiplexing, because I think there's probably 16 sprites. I think when I was counting I got up to 12, didn't I? So there may be 16, because these may be sprites down here, so there's some multiplexing going on. I mean, to be honest, I think these are sprites as well, to be honest. possibly. And that is how I reverse engineered DigDug. So if Docster's on, he can say thanks, because I'm not gonna understand how this works. I'm not going to understand how it works. Docster wanted to do it himself, right? But he couldn't get it to assemble in Kick. He was having loads and loads of issues, and that is how. Yeah, okay, mate. Let's just do it. Shift F6. Control reset. F1. Now I need to be in that one, isn't it? There we go. So F10. There we go. So we've paused it. So as we... No, it's not. They're not sprites. They're actually part of the bitmap. They're actually part of the bitmap. Right, so if I continue it. Look. Can you see when he's breathing, these two disappear. So it's definitely multiplexing. Can you see? So it's definitely multiplexing, and I counted 12 on there. So we've got a simple multiplexer. It's a bitmap game. The background is actually a big giant bitmap. So it goes into bitmap mode and auto generates, because when you look in C64 debugger in the screen in the bitmap mode, oh, let's do it. Let's do it. Change the screen. I want bitmap mode, which is not that one. Oh, what was bitmap mode? Oh, it's on that other screen, isn't it? Hang on. There we go. There we go. So watch, it will, I think it's in here, it's down here. You'll see it draw the screen. So if I reset. Go on, reset. There we go. Look, watch. There's DigDug. So F1. There's the screen. It's a high resolution game, and that's how it builds that. This is it. Because look, you can see it digging down. So it's a high resolution screen, bitmap, and the sprites are sitting on top of it, and that's how they've done it. So this, I've done what I promised, what you guys paid me to do. You edit all the time, okay, mate. Hopefully, is Docster on? Is Docster on? No. I'll ping him in Discord anyway, to let him know that it's done. I'll hand it over to him so he can do his project. But he couldn't, like I say, he couldn't get it working until he told me what the problem was, and it basically was that RTI, because the indirect jump in was going to the wrong byte. but he challenged me to try and reverse engineer it, and that's what I've done. So that's how I reverse engineered DigDug and got it working, and we finished it off in the stream. So I hope you guys enjoyed this. Bit impromptu. We'll get back to doing Myriad, and we'll do some BBC, and I'm gonna try and fire up the Hunchback project, and hopefully I need some graphics. I need some graphics people, so we can get some graphics together, and then we'll start. We'll carry on the streams that I did with the libraries. You know, when we did the joystick library, the multiplexer, the sprite library. See if we can add some more library functions to those to allow us to have the character on the screen and stuff like that. So thanks very much for joining me. Well, Hunchback. So we need Hunchback. We need characters for the screens and stuff like that. So it's I've got some ideas, but this was supposed to be a community thing, and so we need to at least have something to mess around with. Yeah. All right, mate. Well, thank you. I'll get that sorted, and I will see you on the next stream. Thank you very much, guys. Take care. Oh. I'd like to thank all the patrons that are contributing to my channel. Without you guys, I wouldn't be able to do what I'm doing right now. Thank you very much.